Hello everyone, myself Paula Mongwana, Assistant Professor of EC Department at LG Digital Engineering Technology. Welcome to the session of Digital System Design.
It is life in which position we are getting the output is equals to 1. Let us check in truth table. We are getting this one, this and all three ones. Okay, place it inside the 4 variable key map. Position of this one signifies the grouping of all ones. 1, 1, 1, 1. This one is going to be make one group of 2, one group of 4, and the vertical green one is one group of 2. Now, writing of its boolean function. First, we are going to make it for the red one, red line. Okay. What is common in the row wise? A1, B1 bar. See, this bar has been 100. Okay. A1, B1 bar plus the black one. What is common in the row wise? A1, A0, B0 bar. Third winter. And the last one. The green one. What is common in the row wise? A0. Common in the column wise? B1 bar, B0 bar. So we are able to identify that for y2, this is the expression. For y1, it is the expression. And for y2, this is the expression. So if we are going to simplify the expression for y2, it is nothing but a1 is going to be XOR with b1 and a0 is going to be XOR with the b0, x0. Okay, this is the x0. Why? Because for XOR it is a dash b plus a b dash. For x0 it is a dash b dash plus. So this is the logical diagram of 2-bit comparator. Alright. See, from this logical diagram, you are able to identify that we need for a less than b, a1, a0 and b0, and it's a complement form. So a1 bar, a0 bar, b0 going to be ended, a1 bar, b1 is going to be ended, and a0 bar, b1, b0 is going to be ended. The resultant will going to be added with the help of this for. This is the output of a less than b, right? For a equals to b, so a1 dot b1. It is not the AND gate. This represents an XNOR gate. Okay. A1 XNOR B1, A0 XNOR B0. Coming from over here. So A1 is going to be XNOR with the B1. So A1 B1 is going to be applied to the two inputs of XNOR, and A0 B0 are going to be applied to the two inputs of another XNOR. The resultant will be applied to A equals to B. Why? Because over here both the operations are going to be ended. Okay, A1 is going to be x naught with the D1 and A0 is going to be x naught with the D0, and both these terms are ended with each other. So this is the resultant output of Y. Now for A greater than B, so it is A0 B1 bar B0 bar. This is the output. Another is A1 A0 B0 bar and A1 B1 bar. All these outputs are going to be applied to the OR gate. That's why we are getting the output for A greater than B. Alright. So we have seen that a logical diagram of 2-bit comparator. So the 2-bit comparator and the 1-bit comparator has only a single difference, that a single bit magnitude comparator is only compares a single bit with each other. Okay, but for 2-bit comparator, two variables are there. One is for A, one is for B. A has a 2 bits, B has a 2 bits. So the most significant bit of A is going to be compared with the most significant bit of B. And the LSB of A is going to be compared with the LSB of B. Alright, this is the way to realize single bit comparator and the 2-bit comparator. Alright, so we have done in today's session the magnitude comparator. Okay, and we also know that what is the difference between identity comparator and the magnitude comparator. Okay, so this magnitude comparator will give you the 3 output: A equals to B, A less than B, and A greater than B, based on what is my input. Alright, if I am going to design 3-bit digital comparator, that means it will going to compare a 3-bit at a time. That means a 3-bit for A and 3-bit for B. So low significant bit, that means A0, A1, A2 is going to be compared with the B0, B1 and B2 respectively. So I can say that total 6 combinations, so 6 inputs are there. So how many combinations are there? 2 raised to 6. Alright, that means 64 inputs are there. So you need to write it, the 3 outputs Y0, Y1 and the Y2 for the 6 outputs. Okay, total 16 combinations, 64 combinations, 2 raised to 3, that means 3 inputs for A, 3 inputs for B. 3 plus 3, 6. So 2 raised to 6 is 64 combinations of inputs. You need to write the outputs correspondingly. And you need to make a total 3K map: Y1, Y0 and Y2. A equals to B, less than B and A greater than B. But you need to draw a 6 variable K. Alright, and it will increase the number of mean term as well. as number of mean terms are going to increase in the equivalent function, it will increase the numbers of requirement of numbers of logic gates. And as number of logic gates are going to be increased, ultimately it will going to increase the cost of my system. Okay, so that cost will become high as the numbers of bit comparison will be increased. Alright, so we have done the 1 bit and the 2 bit digital magnitude comparator. If you still have any doubt, you can ask me at any time on my mentioned email ID. Till then, thank you for your attention.